As promised, we're back to finish up the chi-squared testing with two-way tables, so contingency tables here. And remember, the two types of tests we're going to look at are tests for independence and tests for homogeneity. So looking here, the key concept is we're going to be analyzing the relationship between two variables for one data set. We're just going to be looking at the tests. Now, they just say in this summary slide, they just say tests for homogeneity. That includes independence. We are not going to look at Fisher's exact test. That's a pretty complex procedure. We're not going to get into it. And we're not going to look at McNamara's test for matched pairs either. We're only going to look at the chi-squared tests for homogeneity and independence. So looking at a two-way table consists of frequency counts for two different variables on one data set. We're looking for relationships between those. So the test for independence is our null hypothesis is always going to be that the row variable and the column variable are independent. There is no relationship between them. The alternative hypothesis then is that they are not independent, that they do have some relationship between them. So our objective is going to be to conduct that test on that contingency table with two variables. So vocabulary, or symbols, I should say here again for us. Just like with our test for goodness of fit, O stands for the observed frequency for each value. E stands for the expected frequency. Now we're going to have to do a little bit more to calculate the expected frequency now that we're looking at two-way tables. R is the number of rows, and C is the number of columns in that contingency table. Only the number of rows and columns that contain data, not the title rows. We're not worried about those. So the requirements are pretty much the same as before. The data is randomly selected from the desired population. Now it has to be arranged as frequency counts in a two-way table, and we have to reasonably expect that each frequency has an expected value of at least 5. Again, the null hypothesis is always going to be that the rows and column variables are independent. And then the alternative, now here they're saying that they are dependent. Most textbooks just word that is not independent. It's a little bit sloppy to say that they are dependent. But remember, the null hypothesis and alternative hypothesis should always be worded such that if one's not true, the other one has to be. So the opposite of independent is not dependent. Now, in most cases, that would be dependent, but it's just a little sloppy to word it that way. So our test statistic, just like with the test for goodness of fit, is going to be the observed value minus the expected value squared, and then divide by the expected value, and we're going to get that for each cell, each entry in our table. Then we add those all up to get our overall test statistic. Now, we had mentioned we have to do a little more work to find the expected value. To get an expected value for each given position in the table, we take the row total for that row of the table and the column total for that column of the table. We're going to multiply those together and then divide that product by the grand total in the table. P-values can be found in our table A4 or from technology. Critical values can be found from that table A4. We still need degrees of freedom. So the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. And of course, it's always a right-tailed test when we're dealing with chi-squared. So this flowchart is similar to the last section. If we have the observed and the expected values are close together, we're going to have a small test statistic and a very large p-value. We will fail to reject the null hypothesis, which means we cannot reject that they are independent. If the values of the expected and observed values are far apart, we're going to get a large test statistic and a small p-value, which could lead us to reject the null hypothesis, which means that we would be rejecting independence, saying they're not independent. So let's take a look at a data set. I'm not a big fan of this data set because it's going to be kind of a controversial topic, but they're looking at the MMR vaccine, the measles, mumps, and rubella vaccine, and the link between vaccine and autism. So our column variables here are vaccinated or unvaccinated, and our row variables are whether the person develops autism or does not end up on the autism spectrum. So I'm going to put this data in Excel. You see I have it listed right here in Excel. One of the first things we need to do is find row totals. Now I left spaces here so that I could use the sum function and not interfere with other any other positions on the table, so that when I do all my calculations, I can put them in the table. Okay, so there's all my row totals and my column totals. Now to find the expected value, I'm going to put that right here. For each of these. So the expected for the unvaccinated would equal row total times column total divided by grand total. I got to put the grand total in here yet. Let me get this. There we go. This expected value is going to equal the row total times the column total divided by the grand total. And we'll do the same here. Equals row times, now we're looking at this column, still divided by the grand total. And here, row total times column total divided by the grand total. Now, all those expected values are bigger than 5, so we're good to go. And you can see, just looking at the data, this value is pretty darn close. Oops. This value is not too far away. This one's not too far away. This is probably the one that percentage-wise is furthest away. If there was no relationship, we'd expect about 18.3 of the unvaccinated children to develop autism. We had 25. But remember, the purpose of this test, that could be that higher number there could be just as a result of an error in our random sampling. So we want to test to see, is that far enough away from the expected value that we could draw some conclusions from this. So let's go ahead. We've got our expected value for each. We can see we filled those in here. That matches up with what we calculated. And this is just talking about the fact that unvaccinated with autism is the one that differs probably the most. But again, we're looking to see, is that far enough that we can draw a significant result from that? So let's go ahead and perform the actual hypothesis test with a 0.05 significance. So our requirements. Based on the description of the study, we are going to assume that these sample was randomly selected. The results are presented in a two-way as frequency counts in a two-way table, and all the expected frequencies are at least 5. We've already checked that. And so, our hypotheses, the null hypothesis is that developing autism and having the vaccine are independent. The alternative is going to be that they are not independent. There might be some link between the two. And we're testing at alpha of 0.05. So let's calculate our test statistic for each. So it's the observed minus the expected squared divided by the expected. So I'm going to go back here and I'm going to do that. This is going to be equal to this minus this squared divided by this. And this will actually work for all of these. So I'm going to find totals here. Add those up. And those two, and then we'll get a sum here. I'm getting a total test statistic here of 3.198 for this data. So adding up all these contributions to the test statistic, the biggest contribution was from that one we flagged earlier, the unvaccinated with autism. But we had a total test statistic of basically 3.2. Now, what would our critical value be? Well, there are 2 rows, autism and no autism, and 2 columns, unvaccinated and vaccinated. So that's 2 by 2. So remember, we subtract 1. So 2 minus 1 is 1. So 1 times 1 is 1 degree of freedom is all we have here. So 1 degree of freedom up top, 0.05 gives us 3.84 is going to be our critical value. So we would reject if we are greater than 3.84. We get the 3.198 was what we just calculated here, is our actual test statistic. So we compare. Here's what the technology gives us. Test statistic 3.198, critical value 3.841. That's not big enough. The p-value then is a 0.074. We can do the p-value here in Excel. So it equals 1 minus the chi-squared distribution. Now this one that's chi-squared distribution.rt, I was playing around with that earlier, and that actually does give the right-tailed. But we're used to everything being left-tailed, so I'll just use this here for now. That is H9, 1 degree of freedom, and true for cumulative. And we get the 0.074 is our p-value. They're saying 0.074 is our p-value. So that is bigger than 0.05, so we failed to reject. So the test statistic is less than the critical value. The test statistic of 3.198 is less than the critical value of 3.841, so we failed to reject. The p-value of 0.074 is bigger than the alpha of 0.05, so that confirms we failed to reject the null hypothesis. So what that means here is that we failed to reject the independence of being vaccinated and developing autism. We can't say that there is a link between the two of them. So this is just restating that, saying we don't have any evidence to reject the idea of those being independent. And once again, interpreting that result in another way. This is used in a lot of different things to link exposure to chemicals and whatever to different diseases. I'm sure you see all sorts of advertisements out there. Were you exposed to Roundup or Prilosec or any product and develop this disorder? This is one of the tests that is used in that. And most of the time, it does not prove to be a significant link unless you play with that value of alpha. And that's what's going on in many of those cases. That, here, if we played with alpha, if we put alpha at 0.10 instead of 0.05, we would have rejected independence. So you can play with that value of alpha and force the data to tell you what you want to hear. There is a dependence between them, and try to make those claims. Well, that's why you set alpha values before you start the test, so that you can't do that at the back end. So the chi-squared test for homogeneity is very similar. The difference is in the test for independence, we selected one big sample. We selected all these bursts, and then we measured both variables on those children. For the test of homogeneity, we have separate populations we're looking at, and we independently select samples from each of those populations. But with the rest of the test itself is the same. We're saying that the proportion of each characteristic in each of those populations is the same. So typically, the test is called a test for homogeneity. We're claiming that the proportions, the null hypothesis is going to be the proportions from each population are the same. The alternative is going to be that at least one of them is different. And the test is going to look exactly like the test for independence. So the procedure, the only difference again is we're going to sample independently from each of those populations, and we're looking to see if they have the same proportion of each characteristic in each of those populations. So the example here is going to be the lost wallet example. We're going to see if different cities across the world, across the country and around the world, if basically looking to see who's the most honest city in the world. They're testing to see if you put a lost wallet out, how many of them would be returned and how many of them would not be returned. So rather than naming the cities, don't want to offend anyone, we're just going to list the cities here as cities A, B, C, D, all the way up through city P. We're going to drop 12 wallets in each city and see how many are returned and not returned for each city. So I actually have this loaded up in Excel right here. I'm going to do row totals here. Row total. So 90 wallets were returned. 102 were not returned. giving us a sum of 192 total wallets that were put out. And we can see 12 wallets put out for each of them. So let's find the expected value. So let's put in here equals 90. Let's see, I want to put the $ in front of the letter here so that doesn't scroll. Times this, and divided by 192. And I'm going to copy that all the way down the row. These should all be the same because the row total is the same, and there's 12 from each column total is also 12. So these are all 5.6. Here then I'm going to do that as equals this, oops, not divided by, times 12 divided by 192, right, 6.4. So this is going to be 6.4 for each of these. So the reason I did those expected frequencies already is we have to make sure that all the expected frequencies are at least 5. Well, these are all at least 5. So, based on the way the study was stated, it's a random sample from each population. The results are expressed as frequency counts in a two-way table, and each of the frequencies is expected to be at least 5. So the null hypothesis is that the lost wallet will be returned as independent of the city. The alternative is that there is a dependence, that they're not the same proportion from one city to the next. You may have detected a little bit of a misprint back here, by the way. They're saying 5.625. It's actually 5.6, and 6.375, which is actually 6.4. They just had a little miscalculation when they were doing their example. So Excel stat, they ran it through. We're going to go through in Excel and show you how to work it in Excel without Excel stat. They get a test statistic, observed of 35 with a critical value of 24.99. So let's find that critical value first. There are, how many cities did we say? There's 16 cities and only 2 rows, returned or not returned. So 16 minus 1 here gives us 15 degrees of freedom in the columns. And 2 rows minus 1 is 1 degree of freedom for the row. So that's 15 degrees of freedom. So if we go here, that's 15. Down here, 0.05 still is going to be right here. 24.996 is our critical value, which is exactly what they have listed down here. 24.996 is the critical value. Let's find that chi-squared test statistic. So for each of these, it's going to equal this value minus this value squared divided by that value. Fill that down. Oops, what did I do wrong there? Hopefully this should fill down. Nope, it doesn't want to do that. So we calculate it for each of those, all 16 cities. And let's do it here for wallet not returned. So you can see we're getting a really small value for each of these, which is to be expected. We are dealing with a lot of different categories here, so each of those being small still could end up being a significant test statistic. So we're going to do the sum of this row here. Giving us 19 there. Sum of this row. I'll expand this so I get my decimal points right. And equals the sum of those two. Giving us the 35.310, which is what we had right here. They said 35.398. We're getting 35.3098. Either way, it's bigger than the critical value, so we rejected the null hypothesis. To get our p-value, equals 1 minus chi-squared distribution. That value, 15 degrees of freedom, and true for cumulative. We get a p-value of 0. That's only because this cell is really small. We get 0.0022. You can see the 5.625 and the 6.4 staying there. The 5.625 was just because of the cell being too small to round it off. The 6.4, though, is the actual expected value there. Anyway, we get our p-value of 0.002, which is what we have here, which is smaller than alpha of 0.05. So that, again, confirms that we're going to reject the null hypothesis. So reject the null hypothesis. The proportion is not the same in each city. There are some cities where you're more likely to get your wallet back than others. Now, moving on from here, we would be looking at Fisher's exact tests and all those others. We said we're not going to do those. So this is as far as we're going to go in this unit. So those are our chi-squared tests. You can see the tests for independence and homogeneity are pretty much the same test. It's just how the data samples are collected that's a little bit different. But the mathematics and the process are exactly the same. And then, of course, our test for goodness of fit was just one variable instead of two. With that, we'll see you next unit.